And welcome to Motors, Generators, and Transformers. Okay, not this kind of transformer, but we use that word a lot, and transform means to change, so it kind of makes sense when we get to it. So let's hop right into it. We're going to try to answer the questions of what's a motor, what's a generator, and what's a transformer. That's our vocabulary: motor, generator, transformer. As always, I encourage you to take notes and upload them for extra credit. I will eventually get to it and check it. Taking notes is helpful, gets it into your brain, gives you an opportunity to think about what you're writing, and gives you an opportunity to review and go back to them if you need to. All right, so let me actually open up the right thing because I'm supposed to be doing this presentation. All right, excuse me. So our first question, what's a motor? We're following up with the video and information from an electromagnet, and so using a motor is an application of an electromagnet. So remember that an electromagnet is when we're using electricity to temporarily magnetize something, and that moving electrons creates a magnetic field. So the video image down at the bottom shows kind of a rough basic setup for this. So what you need in a motor is you need an electromagnet, and that electromagnet hopefully can rotate and spin, and you want to put that inside of a magnetic field. And if you remember how the electromagnet works, and ideally, once we start running electricity through and into the electromagnet, you're going to get a magnetic field generated by the electromagnet. Now, if that magnetic field is inside of another magnetic field, then you have dueling magnetic fields that are going to be able to push one another. Typically, the permanent magnet doesn't really get pushed because it's fixed. However, the electromagnet, since it's allowed to be able to rotate, will rotate, and that's motion. And we can do a lot of different things with motion, particularly if you thought about if we can make the electromagnet bigger, or we could make the permanent magnets bigger, we can get more and more motion. So effectively what a motor is able to do is it allows us to start with some electricity, like a battery or something like that, and change it into motion. This video down here, hopefully it's working that you can see it. It's just kind of a basic setup. You see the south and north poles, so you've got a magnet, and then we have a battery hookup in the middle that's running through some wire. Technically, this is not really looking like an electromagnet, but it basically is, because it's going to be generating a magnetic field in between those two blocks. And so you can see the illustrations trying to show that electrons are moving. And so when these electrons are moving inside of this magnetic field, it's going to cause some pushing. And since this armature is allowed to rotate freely, it will rotate freely. And again, if you can imagine hooking up something to that armature, we might be able to get some useful motion out of it, useful movement out of it, and basically turn it into some kind of a machine when we normally think of a machine, right? So the next question is, what's a generator? Basically, a generator is kind of a backwards motor. In the previous video, what we saw was we started with electricity and turned it into motion. A generator is going to take some motion and turn it into electricity. Now, it still uses a magnet. And so what we're going to do is we're going to take a permanent magnet, like is shown in your illustration from the PhET simulation, and we're going to hopefully put it near a coil of wire. And in theory, if we can get the magnet to rotate, we will be able to generate electricity, even though they're not touching. When you did your PhET simulation, hopefully you saw how this was happening. I'm going to open up the PhET simulation real quick so that we can look at it, and hopefully, again, you can see this. If we turn the water on, we're going to get the magnet spinning. And then when the magnet is spinning, again, what you can see is in the background, the magnetic field that is being generated by the magnet, it starts moving. Now, if we turn it back off, there's still a magnetic field here, but the magnetic field's not moving. Hopefully what you saw in the PhET simulation was a chain of events, is that when the magnet moves, the magnetic field behind it is also going to move. If the magnetic field is moving, the little electrons, which are basically tiny magnets anyway, are also going to respond and move as the magnetic field is moving. Now, again, if the magnet doesn't move, the magnetic field doesn't move, which means the electrons don't move, and we don't have the light come on. So when we get the water flowing, even if it's just a little bit, again, every time the magnet spins, the magnetic field behind it spins. And as the magnetic field continually spins, what we see is that these electrons are continually moving. You do see every once in a while they come to a stop, and that's going to correspond with the magnet kind of changing directions or changing from north to south, which we would call its polarity. But in theory or in practice, what we have here is we have mechanical motion or mechanical energy in terms of the falling water able to generate electricity. Again, you notice nothing's directly touching the wire that you have here in the light. This is kind of called induction because we're not touching it. So even though we don't really have a battery hooked up to this at all, with an alternating spinning magnet, we should be able to get electricity generated through this principle with magnets and such. Okay, so again, a generator is just kind of a backwards motor. We start with mechanical energy, and we're going to be able to generate some electricity from that. And again, you saw this using the PhET simulation there at the very end. So in summary, just think about the difference between a generator and a motor. These two images of a windmill and fan are very similar things, basically, but one is a generator and one's a motor. And you got to think about what goes in and what goes out. So with the windmill, it's capturing the energy from the wind with a purpose to make electricity. So again, the wind is going to cause the blades to rotate. And as the blades rotate, we can get the turning effectively of a magnet. And the movement of that magnet inside of some wires is going to generate electricity. The fan on the right-hand side works pretty much with the exact opposite and reverse. We send electricity into the fan. The electricity that's going into that fan is going to cause magnetic fields to start interacting, and it's going to cause a magnet to rotate or an electromagnet to rotate, and the fan blades are going to be attached to that rotation to generate mechanical energy. So kind of if in doubt about which one of these, what's going on and how to explain it, just think about a generator is generating electricity. A lot of people use an electrical generator in their homes if the power goes out or they're going camping or something. So the whole purpose of that is to produce electricity. So think about what goes in and what goes out. The last little piece here is a transformer. This was a piece of your PhET simulation as well. But what a transformer does is it kind of increases or decreases the voltage through what's called electromagnetic induction. The image I have on the screen here is what you might see on the power line outside your home or outside on the road. And this is kind of is a transformer. So on the inside of it is where some changes in electricity take place. What we need to do with these transformers is that the power lines outside, the power lines that are leading from the power plant to our homes are super high voltage, and we need for that voltage to be reduced when it comes into our house. The reason it's really high voltage, that allows it to travel long distances. One of the things that direct current is not able to do. And again, this is typically happening with alternating current. So how does a transformer work, and what the heck is inside of that little canister looking thing? Well, you effectively have this iron core, if you're looking at the image down here on the right, and you have wires that are coming into the iron core and wrap around one side of it, and then you have wires that are wrapped around the other side that are going the other way. Effectively, the way that this is meant to be drawn is that you have electricity coming in from the left, going around these coils, and you're going to end up having electricity leaving from the right. And again, these aren't really touching each other, even though they have an iron core. It's not that the electricity is being generated through or transferred through the iron core. What we're going to see is, and I'll open up the PhET simulation here in just a second to again show how this works. You'll notice on the left-hand side that there is 110 volts, and on the right-hand side is 220. So this is an example of getting more volts. The one on the bottom is the reverse, and hopefully you can infer how this happens. It has to do with the number of kind of wraps or the number of turns, which is what these tend to be called, on each side. So if you go from very few turns to a lot, the voltage is going to go up. If you go from a lot of turns to a few, the voltage is going to go down. So the top image is going to increase the voltage. The bottom image would end up decreasing the voltage. Now, in this case, the power, which is energy, always stays constant. And so since power is current times voltage, if you end up getting the voltage to go up, then the current's going to have to correspondingly go down. And then it goes into our house, the voltage goes down, which means we end up getting the current going up. So on your PhET simulation, this was tab number 4. And this was the one that started off as a battery, and eventually, with the battery, nothing really happened when you got it close, because again, you have to have a changing magnetic field to generate electricity. But when we change it to an alternating current is always in motion. And so if I kind of move this out of the way, we can see the light bulb lighting up. So what's happening again is this thing that I'm moving around on the left, it's got an alternating current. And so we can see that the current is moving back and forth. And again, that's causing the magnetic field behind it to change. So if I move it close enough to the bulb, it's going to start making the electrons in the bulb wire start moving as well. So again, these wires aren't touching. And again, this is kind of how a transformer works. So a transformer coming for our house, for example, there might be more loops in the transformer coming from the power plant than the loops going into our house. So this would step the voltage down. And you can see when I changed the number of loops, that did have an effect on how bright the bulb was. So all these transformers we have, they can modify the number of loops that are in on both sides of it, and that's going to have an effect on the changes in voltage that's going in or going out of it. Okay, so we're not going to do any math. There can be math with this, but we're not really going to be doing any of that. So in summary, hopefully you've seen what a motor is, and hopefully we've seen what a generator is. Again, a motor is like a fan. Electricity comes out, electricity comes in, motion comes out. A generator does the opposite. With a generator, we have motion to begin with, and we have electricity coming out. And again, a transformer is a way for us to change the voltage and current on an electrical grid of some type. And again, we see those little canisters and boxes are out, and I showed you one image, but there's lots and lots of different transformers on the power grid that we have there. So hopefully this allows you to understand a little bit better about several ways that we can use electricity in a very practical sense, and you should have some questions to go answer after this. Thank you.